All right, here we go with page 2. So it says here, for each of the following compounds listed in problem number 5, that's this guy. It says determine the number of moles of each ion produced, as well as the total number of moles when you have 3 moles of each compound dissociating. So that means, let's change colors here. That means we have 3 moles of this, we have 3 moles of this, and 3 moles of this. You guys get the idea. So that means that if 3 moles of potassium iodide dissociate, right, and we don't use the coefficients if they're 1, but if 3 moles of potassium iodide dissociate, you're going to get 3 moles of potassium and 3 moles of iodine for a total of 6 moles. Same's true here. 3 moles of sodium sulfate, sodium nitrate, and there's no coefficient, so everything's 1 to 1. It means you're going to get 3 moles of this and 3 moles of that for a total of 6 moles. That's all this is asking for. We've got to be a little careful on this one because there's a coefficient of 2. That means 3 moles of magnesium chloride will dissociate into 3 moles of magnesium, but 6 moles of chlorine for a total of 9 moles. And the same is true with this guy because we got a coefficient. So that means that our 3 moles of sodium sulfate would dissociate into 6 moles of sodium and 3 moles of sulfate for a total of 9 moles. All right, so that's how you do that one. That's number 6. Okay. This one, number 7, you've got 3 reactions here. And it's asking us to predict which of these is going to be a precipitate and what the formula equation is going to look like, what the ionic equation is, and what the net ionic equation is, and to identify the precipitate. So let's be careful because we know that this is going to be a double displacement reaction. AX is going to react with BY, and it's going to produce BX and AY, and it doesn't really matter what order we're in. And I'm also not interested in, the right balanced equation and all that stuff. I'm going to do them all the way because, I'm a chemistry teacher and that's what we do. All right, so here we go. We're going to take our A and our X and our B and our Y. We're going to make BX, which is going to be potassium chloride, and we're going to make AY, which is magnesium sulfide. Now they look like this because potassium only has a charge of +1 and chlorine has -1, so you don't need any subscripts. And magnesium has a charge of +2 and sulfur is -2. So the drop and swap would be Mg2S2, but we don't really do that when they're both the same. Okay, and we got to balance this. So because there's a 2 here, we'll put a 2 here, and that also takes care of the 2 here. So that's our balanced equation. All right, easy peasy. And this is also our formula equation. So what we want to do is find out which of these is going to precipitate. So we've got this chart. Remember this guy? And here is our trick. One of our products is potassium chloride, and anything that's got potassium in it is automatically soluble. So that means that this is going to remain aqueous, which is what that means. But here is our mercury sulfide, and it says right here that most sulfides are insoluble, unless they contain sodium, potassium, and ammonium, and calcium and strontium. Well, none of those are this guy. So that means that this is our precipitate. So what does our ionic equation look like? It's going to look like when we dissociate this, and so magnesium and chlorine are going to dissociate, and you're going to get two of them. I don't care if you write them or not. Our potassium sulfide dissociates. We're going to get two potassiums and one sulfide. And I'm going to continue to write the charges in because I'm a chemistry teacher and that's what we do. On our products, you're going to get two potassiums and two chlorines, but the magnesium sulfide does not dissociate. All right, so which of these are our spectator ions? Those are the ones that don't do anything. This guy and this guy don't do anything. They're not part of the precipitate. Magnesium and sulfur are. So our net ionic equation is the magnesium hooking up with the sulfur to make magnesium sulfide. That's the whole thing. Okay? So I'm going to crank through these next two, and I'm not going to be flipping back and forth to the table. You guys can do that, all right? And that'll make these go a little bit more quickly. Okay, so here is number 7b. So our products for our double displacement reaction for 7b, excuse me, are going to look like this. We're going to get sodium chloride and calcium carbonate. All right, that's the balanced equation. Now you should not have to look at the table to determine whether or not sodium chloride is soluble or not. It's soluble, it's salt. We make salt water all the time, but calcium carbonate is not. So what is our ionic equation going to look like? We've got sodium carbonate, which dissociates into sodium and carbonate. We've got calcium chloride, which dissociates into calcium and two chlorines. And our sodium chloride is going to dissociate into two sodiums and two chlorines. But our calcium carbonate, doesn't dissociate. That's the definition of a precipitate. It does not dissociate. So we know the sodium and the chlorine are our spectator ions because they don't do anything except sit there, chillaxing. So what is our net ionic equation going to be without those involved? The CO3 and the calcium to produce calcium carbonate. And that's the whole thing. All right. And the last one is copper 2 chloride and ammonium phosphate. And these are both aqueous. Now, we know that anything that's got ammonium in it is automatically going to be soluble, so we're not worried about that one. But this phosphate, let's go double check, because it says phosphates are insoluble right here, unless they contain sodium and potassium and ammonium. So anything that's got a phosphate in it is going to be our guy. All right, so we know that our products are going to be the result of a double displacement reaction. So that means we're going to get ammonium chloride and copper 2 phosphate. Now, if you're mystified as to how I wrote these formulas, don't panic. I'm not going to make you do that. I'm just looking for close. All right. So I am going to balance it just because I'm that kind of guy, and that means we're going to need a 6 there. So if you're also worried about how I did that, don't worry about it. We're not going to even worry about it. All right. So what happens when our dissociation takes place? We're going to get 3 coppers. We're going to get 6 chlorines. We're going to get 3 ammoniums and 1 phosphate. It's a polyatomic ion, and we don't dissociate them. Our products will be 6 ammoniums and 6 chlorines. And we know that anything that has a phosphate in it does not dissociate. So this big clunky looking thing is our precipitate. So what are our spectator ions? Ones that don't do anything. Those are the ammonium and the chlorine. This guy and this guy. And they don't do anything. Excuse me. Ooh, I should have balanced this better. That needs to be a 2. Because there's a 2 there. You get it? I forgot. Sorry about that. That needs to be then a 6. See, this is how you know that I'm doing this for real and I'm not a robot. Cool. So if those are the spectator ions, these 2 guys, what is the net ionic equation? 3 coppers going into hook up with, that should be a 2 phosphates. And our precipitate, therefore, looks like this. Now, I don't care if you don't have the subscripts, and I don't even care if the equation is balanced. What I'm looking for is, can you tell me which of these is going to be the precipitate? All right. Cool. All right, last couple on this page. This is determining the freezing point depression, delta TF of water for each of these solutions. Okay. So, because these are all in water, and we're talking freezing point, that means the KF is always the same, negative 1.86 degrees Celsius per molal. I will always provide that to you, but if you're looking for where I got it from right here. This is that table that I gave everybody. All right. So we're trying to find the delta TF, and we're going to use this equation. Delta TF equals the KF times the molality. Well, it's water, and so we always know the KF, negative 1.86 degrees Celsius per molal. This one tells us the molality, 1.5, so we don't even have to get all that crazy. We're simply going to bust out our calculator, make sure you have one. And we're going to take negative 1.86 times 1.5. You get negative 2.79 degrees Celsius, because the molality cancels. Okay? Part B is a little more involved because you need to find the molality first. You know that molality is equal to moles over kilograms. You got 0.3 moles in 1 kilogram. 0.3 moles in 1 kilogram is 0.3 molal. So we're simply going to plug it right into our equation. Delta TF is equal to KF times M. You know the KF because it's in the table, and you just found the molality because you're extremely bright people. So negative 1.86 times 0.3 is negative 0.56 degrees Celsius. All right, let's do the last one. Oh no, we've got to find moles. Oh no. Oh. But hey, look at that. Same as this guy, right? Same as this dude right here. So you already know the molar mass. Okay? You already know it. Same as this guy. Sorry, my computer had a bit of a freak out. So I already know the molar mass is 342 grams. So you don't have to get too crazy. The first thing we want to do is find moles. How many moles of C12H22O11? If we have 77 grams, and in 1 mole there are 342 grams. Good thing you brought a calculator, right? So 77 divided by 342 is 0.2. sorry, my computer locked up on me again, is 0.23 moles. According to the